Okay, this is a KwaZulu-Natal question from June 2019. It's the provincial paper. It says here, the diagram below shows a body M, here's the body M, suspended from a ceiling by a string A that is attached to a 2,04 kilo mass by string B that runs freely over a pulley. The strings have negligible mass. It's observed that when the system comes to rest, the angles between string A and B is 90 degrees and the size of angle X is 30 degrees. So if the system is at rest, we are in equilibrium. So 2.1 says, what can be said about the forces acting on point O when the system comes to rest? Well, it's in equilibrium, and if a system is in equilibrium, there is no net force. System is in equilibrium. Okay, now it says to you, draw a closed vector diagram to show all the forces acting at point O. Indicate two angles in your diagram. So usually they ask you to draw a free body diagram, and we would draw the free body diagram very simply by just copying the orientation of the lines, okay, and their magnitude as well as best you can, but not precisely. Like B is going up and to the right, and it's shorter than A, which is going up and to the left. So this is a free body diagram, but it's made up of vectors, and the trick with vectors is a vector has the same magnitude and direction. So I can draw M over here, and as long as I draw it the same length in the same direction, it's still vector M. I can draw it over here, I can draw it over here. They're all vector M. So the thing with vectors is you can pick up and move them and display them wherever you like. So if we draw a closed vector diagram, because all systems in equilibrium can be shown by closed vector diagrams, we're going to end up with a triangle because we've got three forces, and we have to draw the vectors head to tail. Okay, so you have to pick which vector you want to start with, and then just draw the rest of the vectors in their correct magnitude and direction, head to tail with those vectors. So I like to start with the vertical vector. To me, that's the easiest vector to start with because it's vertical, okay? But if I have to indicate two angles in my diagram, and I'm using M as my starting point and M is vertical, I need to now know all of the angles for these vectors from the vertical, because you can see here A is stated from the horizontal over here. B is not stated at all, but if you can see here, can you see here, we have a right angle triangle over here. Okay, you can see that's a right angle triangle. So the angles of a triangle add up to 180. This one's 90. This one here has to be 60 degrees. So let's work out what the angles are from the vertical. Here's my trusty ruler. Okay, let's put this line in here. So I can draw in now a vertical line here. Can you see here? So that's now parallel to M, okay, because we're going to draw M in first, and then these ones will be vertical. So as you can see here, if this is 30 and that thing is horizontal, 90 degrees, this one here must be 60 degrees. Pen, give me a pen. Okay, let's turn the ruler off. This one, this angle here must be 60 degrees. Okay, and then if that is 60, this angle between the vertical and B must be 30 degrees. So now if I want to draw this as a closed vector diagram, I can come and I can start here by drawing first this vector M downwards, okay, and I'm going to draw vector B head to tail. So here comes vector B, which is up and to the right, okay, and then there's vector A off and to the left. I'm also drawing it head to tail. So we know that the angle between vectors A and B is 90 degrees. That's not going to change. But the angle between the vertical, can you see here, this is like parallel lines, and there would be your alternate angles on parallel lines. So this is 30 degrees. Can you see here? Can you see here the alternate angles here? Okay. So vector B is going to now be 30 degrees over here. Why am I writing 60 when it's 30? This is 30 degrees over here. And if we have a look between here and here, if we do the other parallel line, can you see here? Between here, down to here, and up, this angle here is going to be the same as that angle there, which is 60. So the angle between this and the vertical is going to be 60 degrees. So my arrows have made this a little bit untidy. I hope you've drawn something nicely with your ruler. But effectively, we now have a right angled triangle like this. Here is B, here is A, and here is M, and here is my right angle, and this is 30, and this is 60. So this is if we draw it without the arrowheads in, because the arrowheads are very untidy in my drawing. But this would be your closed vector diagram with all the forces just picked up and moved head to tail. Then it says to calculate the mass of body M. So to calculate the mass of body M, we have to look at what we know already. And if we look at this diagram here, what we actually know in this diagram here is this 2,04 kilo mass over here. So if we look at this 2,04 kilo mass, what do we know about this? We know there's only two forces acting on it. We've got the weight acting downwards, and we've got this tension B acting upwards, okay? Now remember, the tension in the string is the same everywhere, it's just in different directions. So this tension going up the string here is exactly the same as that tension going up there. So if we say here for the 2,04 kilo box, or whatever it is, mass, we can say F net equals MA. So T minus FG equals 0. T equals FG. Bearing in mind that this is TB. Yes, it's a tension in string B. So the tension B is going to be 2,04 times 9.8, because it's FG is mg. And so the tension in B is 19,992 newtons. Okay, and I'm not going to round off because I've not finished my calculation. Don't round off until the last step. So now, if you look at my triangle diagram, I now have a value here for B. B is 19,992. But this is part of a right angled triangle. And in order to calculate the mass of this box, I need to know the force in this string, this FG acting downwards. So if I look at my right angle triangle, okay, then I can say to you, here's a 30-degree angle, and B is adjacent to the 30-degree angle. So cos equals adjacent over hypotenuse, and M is my hypotenuse. So the cos of 30 is equal to B over M, okay? But we know B is 19,992, so M is going to be 19,992 over the cos of 30. So you get a value for M, but now it's the force M, big M, not the mass, of 23,08 newtons. But Fg equals mg equals weight. So 23,08 is going to be equal to mass times 9.8. So my mass is going to end up being, by algebra, 2,355, which is 2,36 kilograms.